Hi, everyone, and thank you for joining this session. My name is Dan Sadler. I'll be joined later by Amit Purohit, and we will be presenting this class on motion sensors for power management in connected IoT devices. So let's get started. Okay, so here are the three big ideas that we're going to cover in this presentation. The first is just a statement, which is that wireless battery-operated IoT devices continue to expand into all aspects of our life. This is something that's pretty obvious to everyone who moves around in the world. And because of this, the consequence is that power management becomes a critical factor in the so-called green initiative. So by increasing the battery lifetime of these devices. And so in this presentation, we're going to learn how motion sensors can play a crucial role in this power management for wireless battery-operated devices. Okay, so this is the agenda that we're going to cover. I'm going to start with a brief introduction, and then I'm going to give an overview of the NXP sensors business. And then we're going to drill deeper into the motion sensor segment of the overall sensors business, and going to talk about the segment that Amit and I support, which is the automotive security and convenience and industrial and medical motion sensor segment. We'll talk about the roadmap, and we'll talk about our target markets. I'll talk about why customers choose NXP. And then we'll get into motion sensors for power management, and Amit's going to go into detail on the mission profile studies, including smart sensing with the ultra-wideband or UWB tag mission profile, how a motion sensor is integrated into the ultra-wideband tag, and then we'll look at some other mission profiles such as BLE inhaler and IoT tracker, and then we'll wrap up with a brief summary. Okay, so by way of introduction, we're going to just share a couple of interesting statistics. And basically, the first is that it's estimated by 2025 that there's going to be 76 million devices connected to the Internet of Things. And one forecast yields a figure of more than 23 billion of these being battery-powered IoT devices deployed remotely by 2025. So this is really exciting. Because there's going to be lots of devices to give us information about our environment and to interact with. But you can imagine that the associated energy use and then ultimately energy waste from batteries that these devices are going to use is going to be considerable. So motion sensors can really help reduce this overall power consumption for these battery-powered devices and reduce the waste. And so I hope that by the time we conclude this presentation, you're going to understand how motion sensors play a critical role in these target market segments. And in the mission profiles for the applications that we present, you're going to see specifically how motion sensors are used to manage power and to ultimately reduce battery waste and support this green initiative and really manage our resources in an effective and efficient way. Okay, so let's talk about motion sensors. I'll give you an overview, roadmap, and then we'll talk about the market segments where we're targeting for these products. So before going into motion sensors in general, I have to give a brief overview of the entire business unit, which consists of both motion and pressure sensors, as well as magnetic sensors. So NXP has been producing MEMS-based motion sensors, so that's micro-electromechanical systems, for both motion and pressure detection for over 30 years. And we've shipped, going back to the days of Motorola and Freescale Semiconductor, over 4 billion devices when you include both motion and pressure sensor devices. And from the beginning, and still the current status today, we've been focusing on these devices in automotive and industrial and medical IoT applications. So this is our focus area. I think it's also important to highlight where we're not focusing. We're not focusing on the extreme commodity parts and consumer mobile devices, but really on these high value segments, like I said, automotive and industrial medical. We do support a broad portfolio of products, and where we're going to focus today is mainly on the accelerometers. And we have a variety of these that support a lot of different use cases and market segments. But we also have many other devices that aren't necessarily going to be covered today. Gyroscopes have traditionally been part of our portfolio. We have recently end-of-life a gyroscope, but we are working on development and refresh in gyros and 6DOF or multi-degree of freedom devices. Within our magnetic sensors, we have a new ultra-low power magnetic switch, and we are also developing absolute and differential pressure sensors, tire pressure sensors, and battery pressure sensors for a variety of applications. I do mention here that we are in our 6th generation of airbag sensors. These are our automotive safety products, which again are not really covered in this presentation, as well as we're on our 4th generation of tire pressure sensors. This is really just to give you a sense of our overall market presence in again, a variety of applications well beyond what we're going to discuss today. Okay, so now let's talk specifically about motion sensors, and we'll answer the question, why do you need it? Why do I even need a motion sensor? And they're really essential for a variety of different applications. And I put a few cartoons here to illustrate where they might be needed and how they're used. So first of all, pretty simple question, which way is up? Well, in order to answer this question, you need a device that responds to the gravity field. So a motion sensor does this and can give you the orientation with respect to gravity, so you can tell if a device is upside down or right side up. Now, drilling a little deeper on that, maybe you want to know more than just whether it's upside down or right side up, but what angle is the device at? So that's where an inclinometer comes into play. And so you add a little bit of trigonometry and calculation to this orientation simple application, and now you can tell what angle your device is at. Moving up to a little bit more complex applications, we talk about gesture detection. What am I doing? Did I move a certain way? Did I fall? This is something that, you know, for example, a lot of people have experience with in Apple Watches, Fitbits, etc., but also very important in medical devices. And with some algorithms built on top of a motion sensor or accelerometer, you can determine how a person who's wearing a device is moving. Robotics and navigation. So what direction am I going? Now, these types of applications are going to require more than just an accelerometer. They'll require a gyroscope and potentially a magnetic sensor as well. And they can give you orientation, direction, and are generally used to augment things like GPS for robotics and navigation, either inside an automobile or perhaps walking or other vehicles. Vibration shock, that's another common application for motion sensors. And what's really becoming important nowadays is machine learning or anomaly detection. So based on the vibration signature, can you tell if my equipment is about to fail or is it being abused? So this is another important application for motion sensors. And then finally, moving over to this one here that I've circled, this is really what we're going to focus on in this presentation. And we talk about power management and the idea of reducing waste. So reducing the amount of energy that you use so that you can reduce the times that you have to, both from a convenience perspective and also from a managing our natural resources perspective, reduce the number of times you have to change a battery. So there's a number of applications that rely on wake up on motion. So I don't necessarily need to be operating the device at its full power consumption unless it's moving. A couple simple examples: a remote control device, a key fob device. You don't really need the wireless interfaces to be operating unless the device is moving. So if you can use a motion sensor to detect that motion when you started moving the device and when you've stopped moving the device, you can use these to efficiently manage power. And we'll talk about that a little bit today, or actually in some significant detail today in the presentation.
Okay, so understanding the applications that these products support, the question really remains is what products does NXP offer that can support these types of applications that were discussed? And so what I'd like to do right now is go through the roadmap for the automotive convenience and security and industrial medical segment. I will not be, as I mentioned, focusing on pressure sensors. I will not be focusing on automotive safety sensors, but I want to give you a feel for the types of devices that can be used in the applications that were presented in the prior slide. And really, in general, all of these devices are what we would call low-G accelerometers. They operate in the range of 2 to 16G and are generally quite good for applications such as orientation detection, basic human motion detection, vibration monitoring in machines and equipment, etc. So a really good fit for the applications that we discussed. So if I look at the products on the left-hand side, this list of products here is what's currently in production. And these are products that have been offered for some time by NXP. I'm not going to go into great detail on those. What I do want to talk about is this other product family in the green box here, the Gemini Timandra family. And the green box does indicate that these products are also in production. And you can see by the timing that the right edge of this aligns with the release timing. And these products were just recently launched within the last within the second quarter of 2022. So we're going to talk about those a little bit more on the next slides, but basically this includes a family of 4 different product numbers and really covers a wide range of applications. And I like to refer to this as basically a general purpose 3-axis accelerometer, very good for basic sensing in all the types of applications that were presented previously. And you can see here that I'm noting that it was qualified in Q1 of 2022. Now, if we look forward, look at the next generation product. Its code name is Chiron here, and you see the part numbers listed here. This is basically planned as a derivative of the Gemini Timandra family, and really is looking at optimized temperature performance, so precision angle use cases. So there are going to be a series of applications on the prior slide that perhaps need better accuracy over a wide temperature range, and this product here is going to provide that additional capability that may be needed in those use cases. And then if we look a little bit further out, the next generation, what I call ultra low power accelerometer is called Solstice, and that's something where we're really looking at this family here and saying it's already a market leader in terms of ultra low power, as I'll show on the one pagers that describe these products. But what the Solstice product is doing is actually driving that current consumption even lower, and it's based on some new IP that NXP has developed in that space. And then the other really important future product, one of the applications that I mentioned previously was vibration monitoring, and so clearly the general purpose accelerometer can be useful in that regard. But when you really want to sense very high frequency signals, you're going to need an accelerometer that goes beyond the kilohertz bandwidth that you can get with the general purpose accelerometer. And this is a new product that we're targeting for out in the 2025 timeframe that's really going to be targeted at vibration sensing with a wider bandwidth than is generally available in low-G accelerometers today.
So with those devices as a backdrop, let's now look at the market segments where we're involved. And again, I'll just reiterate that we're looking at the industrial and medical segment of the IoT market, not the highly commoditized consumer and mobile market. So we're interested in things like industrial, transportation, patient care, connected homes, conservation, factory and automation, and building and control. And what we see some of these driving factors to sensor proliferation. First of all, human interaction. There's lots more interaction between the human and automated devices, whether it be gesture, tapping, orientation, vibration. I mentioned machine learning, anomaly detection, looking at vibration signals and trying to detect preventative maintenance. And then really the class of applications that we're going to talk about, which is intelligent sensors for managing power in remote devices. And then if we look at the other relevant segment here, which is the automotive security and convenience, which is very similar, I'd say, in terms of use cases and also in terms of quality requirements for the industrial and medical segment. We have numerous applications that we're seeing pop up over the last few years and continue to develop in the automotive segment. Passive keyless entry with key fobs is probably the prime example of a recent application that's been improved with the addition of a motion sensor. So you can imagine these devices have a low frequency, a high frequency radio that's always on, looking for the car so that it knows when to unlock or lock the vehicle. But you really don't want that radio on all the time. Not only is it using power that you don't want to use, but it also has proven to be a security issue, as thieves have been known to try to sniff these signals and steal the signal. For example, when your key fob is in your home and resting idly. So this is where a motion sensor can both provide the important power management aspect, as well as the relay attack prevention. So if the radio is not on, you can't actually sense the signal and you can't steal the signal. And then we see a lot of other applications, car alarms, e-call, surround view cameras. These are things where you're trying to detect motion or movement of the vehicle, and then smart doors and latches where you're looking at inclination of enclosures, whether they be doors, trunks, or internal enclosures. Okay, so why do customers choose NXP? Obviously, this is a very competitive field, and we do compete against some formidable competitors. But I think that the biggest reason, and what I've been talking about specifically in these applications, is we are an industry leader in terms of low power. The current draw on these devices that I'm going to talk about is extremely low, hundreds of nanoamps to 1 microamp in terms of what's required to wake up the device. We have a really nice development ecosystem that makes evaluation and development extremely easy. And we have a parallel presentation that Amit is also going to cover, which is going to address the elements of our ecosystem. System solution with NXP, in addition to the sensors that are important, NXP has the wireless connectivity devices, the microcontrollers, and we do have a variety of different reference designs and systems developed with these, I guess, system solutions in mind. And Amit's going to cover a couple of these in the latter part of the presentation. And often we're the only product that actually meets the specification and reliability requirements of the application. This is particularly true in automotive applications. Often it's true in the automotive safety airbag deployment applications, but it's also really true in the key fob example that I gave. NXP uniquely combines this low power accelerometer with a very robust device that is able to withstand shocks up to 10,000 G and still survive. And you can imagine people handle their key fobs very roughly, dropping them on the floor and such. So the device has to not only have the low power and the performance capability, but also the robustness. What's next? We're looking to expand into these other automotive applications, some of which I mentioned: car alarm, baby seat monitor, under hood lamp. That's an inclinometer type application. And then in the IoT, we're just continuing to look at these power management devices, and then how can we expand to, say, vibration monitoring types of applications as well.
Okay, so what you see here is the one pager for the for two products in the Gemini Thermandra family, FXLS8964 and 8967. And on the next page, I'm going to talk about the third product in that family of parts, which is the 8964. Now, these two part numbers, these two products are really targeted for the automotive market. And again, as I mentioned, security and convenience, not safety applications. Well, the really key features and the most important aspects of this product is that first of all, it is fully pin and software compatible replacement for the 8962. So if we're talking about, this is a legacy part that was designed into a lot of automotive key fob applications, and this part family is designed to be pin and software compatible to allow for easy drop-in replacement on those applications. But really, when we look at what differentiates this part from others in the market, I would call to attention three specific features, which I'm going to highlight one by one here. Ultra low power, so less than 1 microamp in low power wake up mode. We're talking about hundreds of nanoamps to sense motion. And the other important, I would say, parallel feature to that is the sensor data change detection block. So this is basically a highly configurable digital window comparator, and it allows for really easy implementation within the device. So not having to task the microcontroller's resources to really just detect and issue an interrupt on motion. So these two features really work hand in hand: the ultra low power and then that sensing of motion, triggering an interrupt for the rest of the system to react to. And then the third important feature, which highlights another key differentiator in the NXP products, is the self-test diagnostic. Now, self-test is something that is used generally in all accelerometers, but the thing that's very important here, and the real differentiating factor from an NXP IP perspective, is that the self-test diagnostic can be run in the field, and it's not affected by device orientation or motion. And this is in contrast to general self-test, which can be run at the end of a line, end of line testing on our customer lines to determine if the device is functioning or not. This is something that can give you an assessment of the health of the device in the field. And it's really important for these wake-up applications, because the way these work is you're generally shutting down radios and other important components and waiting for them to wake up when you get a motion signal. So before you shut those components down, you really need to make sure that your motion sensor is working properly. And if it's not, you can take mitigation actions. Additionally, we've got multiple digital interfaces, a very small package, extended temperature range, and EMC Class 3 compliance. And the applications here are motion detection for key fobs and telematics, car alarm, electrified doors, other things in the automotive space. I will mention here that the main difference between these two part numbers and the part number on the next slide that I'm going to talk about is really the way that they're tested and the specification that they're tested to. They all share a common signal conditioning ASIC, a common MEMS, a common package. They're all software compatible, so it really comes down to minor differences in the test specification. And as I mentioned previously, these products are now qualified. We do have samples available. There's an automotive PPAP for both part numbers, and the production release is now. So I won't go into a lot of detail on this slide, because really, as I mentioned, this is a sister product of the other two, the 8974. Its code name is Tamandra, and this is really target for the industrial medical market. As you can see, the key features are identical, so there's really no reason to go through all of those again. In essence, the device operates exactly like the two devices on the previous slide, with the exception that, like I said, all three are tested to slightly different specifications on some key parameters, and those are very obvious in the data sheets. And you can see the target applications here. And again, this product is released. Samples are available, as well as production material.
So finally, I conclude with a block diagram, which you could find this in the data sheet. It just simply shows a little bit of what's under the hood of the device, multiple MEMS transducers to sense lateral or XY motion, as well as Z motion, multiplexed through a capacitance to voltage converter along with a temperature sensor, and then the digital signals available on the I2C or SPI interface, with a variety of different features and interrupts available to support unique applications and to really simplify the development required. So with that, I'm going to conclude my portion of the presentation, and I'm going to turn it over to Amit. So I do thank everyone for their time and attention, and enjoy the rest of the presentation.
Thank you, Dan. Hello, everyone. My name is Amit Purohit, and I will be presenting next set of slides. In the next section, we'll be learning more about value add of adding a motion sensor for power management in connected IoT devices. Please continue entering your questions in the question box below, and we will have a subject matter expert available after the presentation to answer any questions that you may have. So let's first understand why we need power management and why it is very critical for the battery operated IoT devices. Dan already covered a brief about that, but I would like to put more emphasis on that before we move on. So as we know that, most of the IoT devices are placed in remote locations and they rely on batteries, and it is very critical to have longer battery life for them, right? And you may think of a battery, tiny battery, and it may not convince you that how it's detrimental to the environment. But once you know how many of these things are being produced every year and how many end up in the landfills, that's when you will realize and it will change your mind. As Dan mentioned, some fact figures that there will be approximately 23 billion estimated battery IoT devices in the market by 2025. Now you can think of the associated energy use and waste of batteries, right? Uh, when we look at the latest technologies that we have, including microcontrollers and communication protocols, we know that we have very advanced microcontrollers now supporting very low power modes. The communication protocols are getting optimized day by day. They also support many other features. But depending on the use cases, the end use case, the wireless connectivity itself can consume between 40 to 70% of the total power consumption of those devices. Now, can we do something else to improve that? Yes, definitely we can do that. A motion sensor there can help, and that's what we're going to discuss in the next few slides. So I'm just giving a few pointers here, and this will give you a brief introduction to you on what topics we'll be talking in next few slides. So in those remotely installed IoT devices, do we really need motion gesture-based wake up so that you can then direct MCU to go into the ultra low power, or you want to limit or reduce the RX or TX time of the communication protocol because that's where it is taking the most of the power consumption. Do we really need to transmit every data, or we only want to transmit or receive when we have any meaningful data available or on motion anomalies? In some of the use cases, we can have an acceptable lag in connection. For example, you may have few seconds to restore the connection and you can go into very deep sleep. For those kind of scenarios, probably you will have a very significant power optimization done using motion sensors. So the next few slides will talk that how motion sensor based on the assumed use cases will present you can increase the battery lifetime by 2x to 4x. And let's go to the next slides and learn how. Before we go further into the details of those mission profiles, let me give a brief history on how NXP is actively focusing on system solutions to create their new product definitions. NXP has been focusing to now create system solutions combining multiple NXP technologies to offer a ready-to-market solution for customers. It is not only helping our customers, but it is also helping internal teams to define a better product definitions and come up with new products. And from the sensors group, from the motion sensors group, we have been very active in integrating sensor features in multiple use cases across different NXP technologies for industrial, medical IoT, and auto non-safety applications. So this was a brief introduction on the activities that are being supported. And in the next session, we'll be talking about few mission profiles to demonstrate how motion sensor can help in power optimizations. And we'll be talking about some of those system solutions where we have collaborated with other business lines within NXP. Before we move on, I want to make a note here that the power consumption numbers that we present in next few slides are only for giving you approximate values, describing how you can achieve power optimizations based on those average values using a motion sensor in your design. The actual values, the actual performance numbers may or may not vary based on your use case. Let's start with the first mission profile study. So we do have a ultra wideband smart sensing tag design. It's a system solution or reference design, and it is based on ultra wideband and Bluetooth low energy connectivity. And we have added a motion sensor and a low power accelerometer in the design. And the main idea and the main application of this kind of reference design is to provide accurate positioning data of the device for indoor localization. So this, as you can see this in the picture, this is like a coin cell size hardware which you can attach to any of your device at home, at your workplace, or anywhere. And then you can very accurately position that device in the accuracy of few centimeters. Now you would be wondering that why we need accelerometer in such kind of designs. I mean, ultra wideband for the core application, ultra wideband and BLE MCU is good enough. And you are right. I mean, for the core functionality, we don't need accelerometer. Probably we can do we are good with ultra wideband and BLE technologies, but then we'll tell you that how accelerometer is helping in such design. So when we added an accelerometer to such design, it is not only enabling few other alerts or few other new use cases like theft and tamper detection, but the main use case of an accelerometer is to optimize the battery lifetime. Now these kind of devices, because they do ultra wideband ranging and BLE transmissions, they can be very power hungry. So we learn now that how in this design we can use a motion sensor to reduce the battery life, so to increase the battery life by 2x to 4x. Now, in this next slide, I'm talking about a real life application of ultra wideband sensing tag. Now, think of a situation where we have a smart device for post-COVID safer workplace scenario. It can be a smart workplace device as well. So your employer is providing a ultra wideband sensing tag kind of device to every employee when they enter the office, and to make sure that they can practice social distancing and contribute towards safer workplace, right? And the idea is that that kind of a tag can determine nearby tags or nearby employees who are carrying those tags, their relative positions using precise localization capabilities using ultra wideband ranging. And they can raise alerts to maintain safe social distancing, right? Again, I mean, now once you learn about this real-time application or real-life application, you would wonder that, I mean, this can be very power hungry because the system need to be on every time. You never know when you can cross the safer limits or social distancing limit. So how we can improve, and by the way, these tags are operated by batteries, cell batteries. So if you think of a situation where you have 500 or hundreds of employees and everybody is getting tags every day, and the power consumption is so high that you need to change or throw the battery every other day. How much battery wastage we can have, right? Now let's start talking about mission profile and take some assumptions. So we are assuming, and it's a very valid assumption, that every employee spends close to 8 hours at their workplace. Close to 6 hours working or sitting where they can be in no motion or safe mode. Once they are not moving and your workplace is covering that safe workplace location, then it can be treated as a safe mode. And around, let's say, 2 hours at some other places like in cafeteria, in near to coffee machine area, or some phone booth, or some other area where you can show some motion, you are moving, and hence it can be a risk mode because you can cross people around, or you can cross the safe social distancing area or zone. Now with this assumption, we'll talk more, and we'll describe you that how adding a motion sensor in this scenario can not only create some other use cases, but particularly help in reducing the power wastage or increasing the battery lifetime by 4x for A, which is ultra wideband only mode, and close to 2x for ultra wideband plus BLE mode. So let's learn more about these modes, and then we'll describe you some profile numbers. So as I said, these kind of tags or variable units can be powered by coin cell battery. Let's take an example of CR2032, which is a 225 mAh battery. Right, and I briefly mentioned about two modes. So these kind of devices can operate in two modes. They can operate in mode A, which is ultra wideband only mode. So in this mode, it's a very raw mode where ultra wideband ranging is always on. Right, so it is always detecting nearby tags or variables and the relative positions and alerting employees that you are within the safe distance or not. Now the other mode can be ultra wideband plus BLE mode. This is I would say slightly optimized mode where the ultra wideband ranging is not always on, but BLE connectivity is advertising all the time. So you can say that the BLE connection is always on and it is advertising and trying to detect nearby tags, BLE transmissions. And it activates ultra wideband ranging by measuring whether the distance between nearby tags are decreasing beyond a threshold, right? So that means it's a if you can see that the mode B is already an optimized mode. But can we do something else to further optimize the power and reduce the battery wastage? So we'll see that in next few slides. On this slide, you also see some numbers. So let me remind you again that these numbers are approximate numbers, and the numbers may or may not be the same for your actual applications, but these are the profiling data we have got for individual operations. Like for ultra wideband ranging, when it is in active mode, we are trying to highlight an average minimum consumption, which is close to 15 milliamps. Similarly, in the idle mode, ultra wideband ranging can still take close to 1 milliamp. When BLE advertising or beaconing is happening in active mode, it can take close to 2 milliamps. In an idle mode, let's say 0.5 milliamps or 500 nanoamps. And motion sensor in the active mode running at 100-200 hertz can take close to 10 microamps. And in idle mode, it can take close to 2 microamps. So with these average values in mind, let's move on and see how for different modes of operation for this mission profile, adding a motion sensor can help. So let's consider mode A. As I mentioned, that mode A is ultra wideband only mode, and it is basically in this mode, the ultra wideband ranging is always on. So it is always detecting nearby tags and their relative positions and alerting employees. So based on our assumption, employee worked around 8 hours, and if all the time ultra wideband ranging is on, that means it is active. It is taking close to 15 milliamps every time on an average. So assuming that a CR2032 battery is powering those devices with a 15% discharge safety, the battery lifetime will be close to 12 to 13 hours. So you can think of, in this mode, the battery will last only for 1 to 1.5 days. So every 1 to 1.5 days, you need to change the battery, throw the battery, or recharge the battery, right? Now think of how many employees we have. If you have hundreds of employees, so you are throwing away those number of batteries in 1.5 days. Can we improve on that? Yes, so in the case 2, we can see that now if we add a motion sensor, which is enabling ultra low power motion wake up feature to save power consumption, right? Now, think of two situations where we took an assumption that 6 hours, employee is sitting at his desk working in the safe zone. So he's showing no motion, very little motion, right? Can we detect that situation autonomously? Yes, we can do that through motion sensor. And once we do that, that there is no motion, the motion sensor can automatically put the ultra wideband to idle mode and go to sleep as well. So you can see that in the ultra wideband idle mode, no movement, safe zone, we are only taking 1 milliamps, which is the idle power consumption, idle mode power consumption for ultra wideband, and close to 2 microamps for motion sensor for 6 hours. And for 2 hours, where the employee is showing a motion, or we can call that as a risk zone, the motion sensor detects a motion and it goes to active mode, and it also activates ultra wideband ranging. So these numbers show you 15 milliamps for ultra wideband ranging active and 10 microamps for sensor active. And with the same calculation, you can see that the same battery with 15% discharge safety, the battery runtime will be increased to 42 to 43 hours. That is approximately 3x to 4x saving, right? That's a huge saving. So now your hundreds of employees, you were throwing away batteries without a motion sensor in their design every 1.5 days. Now it can run for more than a week. So you can understand the difference here. Now let's talk about the mode B. So I already mentioned that mode B is optimized mode, power optimized mode, in terms of as you compare with mode A, because BLE is taking less power, of course, than ultra wideband, and BLE is always on. Ultra wideband is not always on, right? So let's talk about this situation and take an assumption that out of 8 hours, 50, and let's assume that 50% of the time the BLE advertising is happening, and 50% of the time ultra wideband ranging is there, right? So when the BLE advertising is happening, it is taking 2 milliamps because ultra wideband is in 1 milliamps for the ultra wideband idle mode because ultra wideband is not ranging, and 2 milliamps for the active mode of BLE advertising for 4 hours. And when it detects that the distance is decreasing beyond a certain threshold, it activates ultra wideband ranging. So at that moment, the ultra wideband is in active mode taking 50 milliamps, and you don't need BLE at that time, so it can be in idle mode. So you're taking 0.5 milliamps for 4 hours. Now with these data points in mind, the CR2032 battery runtime will be approximately 20 hours. So still you can see that although it was close to 12-13 hours for mode A, mode B is giving you 8 more hours for the battery. It's a good saving. Can we do more, right? So yeah, so we can do more. So in case 2, we are highlighting how we can further optimize it. Now, if you add a motion sensor with ultra low power motion wake up feature, right? What we can do is, and again we consider what an assumption, right? That 6 hours no movement, 2 hours movement, so risk zone. So in the movement, when there is no movement and you're in the safe zone, there's no need to have BLE advertising. There's no need to do ultra wideband ranging, right? So motion sensor can automatically detect that there's no motion for certain period of time, and it can autonomously go to sleep mode, putting the device ultra wideband to idle and BLE into idle. So the last row describes those numbers. Now within the 2 hours of risk zone, based on our earlier assumption that let's divide 50% advertising happening and 50% of the time ultra wideband ranging happening. So when BLE advertising is happening, 2 milliamps taken by BLE advertising, 1 milliamps taken up by ultra wideband, and 2 microamps by motion sensor. But when we activate the ultra wideband ranging, 15 milliamps taken by ultra wideband, 0.5 milliamps by BLE, and 10 microamps by motion sensor for 1 hour. Now, if you do the calculation and assuming CR2032 discharge safety for 15%, your battery lifetime can be increased to 38 or 39 hours. That is close to 2x for mode B as well. So although we identified that mode B is an optimized power optimized mode, motion sensor is still helping in 2x battery saving even in that mode, right? So that's how the motion sensor is playing a critical role, or can play a critical role in power optimizations. Now we talked about one profile. We have some other profiles as well. So we have a medical IoT based reference design. It's called Smart Sensing BLE Inhaler. It's basically an automated medicine dispensation system based on detection of patient's tidal breathing pattern using a biocompatible pressure sensor. But it also has a motion sensor to make sure that the posture or the inhaler position or tilt position is correct to get the exact amount of prescribed dosage. Right now, if you think about this reference design or solution, you will think that, I mean, these can be battery powered, these can be powered by batteries which can be recharged, right? In either case, you would not like to do recharge in every few hours for such kind of devices because the usage is not that much, right? But we can tell you that, I mean, if it is based on Bluetooth low energy as well, then a periodic wake up or any kind of feature that the optimized protocol may have, still it might be power hungry, right? And we have some data, but we are just showing the summary here based on this assumption again. So let's assume that patient who is using this inhaler, they are only using it for 2 to 3 times a day, right? That is max they can use, and maybe they are using it 10 minutes each every time, right? Rest of the day, I mean, rest of the time, the inhaler is inactive. Do we really need to have power wastage during that time? No, ideally should not. And that's where the motion sensor can help, right? So motion sensor can detect ultra low power wake up, or whether it's based on just a pickup, whether the patient picks up this device or they shake the device. That can be a trigger for the device to activate, right? So motion sensor can detect whether it's in motion for motion gesture like a pickup or a shake, and it can activate the device, right? Or it can automatically detect that for a certain period of time there is no motion, and it can put the device into deep sleep. There's no even connection needed, right? So this particular example, if you remember in my earlier slide, we mentioned that in some use cases, you may have flexibility to have some kind of delay, applicable delay while you restore your connection. This is such kind of application, right? So you can actually get to very low power consumption when you are in the inactive or idle mode. And we have seen, based on some of those average numbers, the mission profiling tells us that just by adding a low power accelerometer in such designs, not only helping in creating more use cases like getting to the correct posture of the or correct tilt of the device, it also can increase the battery lifetime by 2.5x to 3x. Let's move on and talk about one more application. So asset tracking is a very good application for motion sensors, and of course we need connectivity there, right? So nowadays we are having a lot of low cost asset tracker applications for smart logistics application, which can monitor shocks, tilts, free fall. It can also check valid temperature, humidity ranges of the shipped assets, right? Now we have a reference design which also integrates Sigfox protocol. Again, now when we will talk more on Sigfox, Sigfox is a really low power consumption protocol. We'll still see whether we can still do some optimization there. So when you learn about this Sigfox protocol, you may learn that if you compare with other protocols like BLE or like ultra wideband or SIG or Wi-Fi, it's a very low power protocol, right? It's still taking very low power. But can we do something about it? I mean, can we still do further optimizations? We'll learn about that now. So in this design, it also uses real-time geolocalization using GPS receiver and Sigfox triangulation scheme to know the approximate location of the shipped asset. So in summary, this kind of a system solution can not only tell you what has happened with your shipped asset, how the handling was during the shipment, it can also help you track the shipment using Sigfox and GPS receivers. Now, I'm just giving a brief about the Sigfox messaging, and you will learn that how now motion sensor can help improve the battery life of such devices. So while Sigfox is sending GPS coordinates and motion events for any kind of events that might have occurred, like shocks, tilts, free fall, or temperature, humidity if it is out of range, Sigfox send an uplink message every 10 minutes. Although it's a very small message, it takes 6 seconds, and every 10 minutes you need to send it. It also basically some of the messages also is basically a keep alive message to say that the connection is alive. Now let's make an assumption that we really need to do that. I mean, let's think of a situation where we don't need to send a Sigfox uplink message every 10 minutes because it's not needed. I mean, there's no point in providing GPS coordinates every 10 minutes, or you never know if there has been any kind of motion events or change in temperature or humidity. Then why you want to send a message every 10 minutes? Can we reduce that frequency, right? Now so we have to send a keep alive message, as I said, to make sure that the connection is alive. But communication protocol allows us that if that can be sent once a day or twice a day, it should be good enough to say that the connection is alive. So let's assume a situation that tracker need to only send uplink message when there's an anomaly detected, whether in terms of motion gestures like shocks, tilts, free fall, right, or a change in the valid ranges of acceptable ranges of temperature and humidity. Then only we want to trigger the Sigfox uplink message along with the GPS coordinates where it happened. And we can have, let's say, one message, keep alive message per day. If we limit to that, we have the numbers to show that the low power accelerometer in such designs can increase the battery life by 2.5x. So think of this now. Sigfox itself with a 2 AAA batteries can run for close to 90 days. It's good enough, right? I mean, so it's such a low power protocol that it can let you run your batteries for 90 days, even it is sending for every 10 minutes, message sending for every 10 minutes. But just by adding a motion sensor and on a specific use case basis, the battery lifetime can be increased by 2.5x. That's a huge saving, top of already what we can achieve with Sigfox. Right, so these are some of the applications we wanted to talk about in today's session. And so let me summarize, and I hope that you enjoyed this session and learned about NXP's history of supplying motion sensors into automotive, industrial, and market segments. And you also learned how motion sensors are transforming a new set of applications, and particularly ideal for applications where low power wake up can help in power management, right? And based on some of the mission profiles or use cases that we described how motion sensor can help achieve 2x to 4x power savings and reduce battery wastage. Again, thank you very much for for joining this session today with Dan and myself. Don't forget to visit our virtual showroom and learn how NXP see technology advancing and automating our future. For more details, please visit showroom.nxp.com.
Okay, so with that, I'd like to thank everyone for joining the class. If you have any additional questions, please reach out to your NXP representative or ask your question in the featured community below this video. Thank you very much.